Now for the useful stuff. The Fundamental Theorem of Calculus Part 2 is going to be your shortcut for finding integrals. You do not have to do limits of Riemann sums for the rest of your life. Okay, so the Fundamental Theorem of Calculus Part 2 tells us, as long as you start with a continuous function on the interval of integration, then when you do the definite integral from a to b of a function, that will equal, and what's this capital F? Capital F of b minus capital F of a, where capital F is any antiderivative. So basically, you're just going to take an antiderivative of your integrand, and then you'll plug in the top limit of integration, the lower limit of integration, and subtract. So that is the useful part of the fundamental theorem of calculus. So let's just write that down in words, right? So to evaluate a definite integral, find an antiderivative of the integrand, then evaluate that antiderivative at the limits of integration and subtract. So since it's subtraction, order matters. So make sure you're doing f of b minus f of a. Okay, and then I just want to give you a little notation. This f of b minus f of a can be written in a different way, and you'll see how we integrate this into our problems. So if I have the function and I write either a solid line with the b here and the a there, that is one way to write f of b minus f of a. Or some books or some students' teachers, instead of a solid line, they write it as a bracket. Okay. So that is just a notation, a way to kind of keep track of where you are. And let me show you how you're going to use that in the next couple of examples. So we're going to apply this fundamental theorem, and we're going to evaluate these integrals without having to do limits of Riemann sums. Yay! So the first thing we're going to do is we're going to start by taking an antiderivative. So an antiderivative of this polynomial, term by term. We have x to the fourth minus x to the third plus 3x squared. Now, in general, when we do an antiderivative, what would we need to add right there? Plus c, right? But in this case, if you go back to the statement of the fundamental theorem of calculus, you'll notice that it says any antiderivative. So you have a choice. You can pick whatever c you want. And the best c to pick is definitely 0, right? You don't need to add an extra term to your calculations. So when you're doing antiderivatives for definite integrals, you can leave off the c and just basically be choosing the c equals 0. And then here is the point where we're going to use this notation to basically hold our place. Here's the antiderivative. Now we need to plug this number in, subtract, plug this number in. Right? So you can see how that's kind of a handy tool at that step. So I'll plug in the upper limit of integration, which is 2. And then subtract lower limit of integration, which is 1. And then you just have to do that calculation. And you end up with 17. Okay. Let's try the next one. So we have the integral from 0 to 4 of 4 minus x times the square root of x. Now, when you look at that, do you immediately know what an antiderivative is? In fact, do we have a way at this point to do an antiderivative of a product? We don't, right? So what technique are we going to need to do first to this integrand? We're going to need to distribute. Because then you can do the antiderivative. I'll just write anti-der, term by term. So what I'm saying is I'm going to leave that 0 and 4, and then I'll have 4x to the 1/2 minus x to the 3/2. And now I'm ready to take the antiderivative term by term. So that will give me 4 times, using my power rule, I'll add 1 to the exponent and then flip that new exponent as my coefficient, add 1 to my exponent, and then flip that exponent for my coefficient. Okay, so that gives me 8/3. And again, x to the 3/2, I'm going to go ahead and put in my 4. So 4 to the 3/2 and 2/5, 4 to the 5/2. We'll talk about how to evaluate that in just a second. Minus, well, what happens when I plug in 0? 0 to the 3/2 and 0 to the 5/2 is 0. So that whole second part will be 0. That's nice. All right, so I know that you could plug 4 to the 3/2 into your calculator. That's great. But, you know, we're always striving to make some sense numerically and algebraically of these numbers. So remember that what this means, the power is the top number and the root is the bottom number. So it's like the square root of 4, which you know what that is, to the 3rd power. Okay. So the square root of 4 would be 2. 2 to the 3rd is 8. So this is 8. And then same thing here. The square root of 4 would be 2. 2 to the 5th is. So like I said, I know you can plug that into your calculator. I'm not telling you never to do that. But at the same time, we want to make sure we're numerically proficient. Right? And sometimes I'm just too lazy to get my calculator out. So I have 64/3 minus 64/5. And if you common denominator that, you will get 128 out of 15. I will tell you that most often you're going to be doing a lot of this stuff in Calc 2. There's very few Calc 2 teachers who want you to give them the decimal. Instead, they want you to give them the exact answer. I actually think that might, can that be simplified? No, maybe not. Okay, so you have the general idea. Why don't you pause the video and try numbers 3 and 4. How'd it go? Those were pretty simple ones. I was trying to just give you basic antiderivatives. So the antiderivative of cosine is sine. I plug in the pi, which is 0. Sine of pi is 0. Sine of 0 is 0. So 0 minus 0 is still 0. Don't forget, when you have x to the -1, it's not a power rule. The antiderivative of 1 over x, or x to the -1, is the ln of the absolute value of x. Now, granted, it doesn't matter the absolute values here because the two numbers we're plugging in are positive, but these could have been negative and it would have been okay because we would have just used the absolute value. Okay, so I have ln of 6 minus ln of 3. Since I'm subtracting 2 ln's, I can convert that to ln of 6 over 3, which is the ln of 2. All right, a couple more here to try. I'm going to go ahead and do the same thing and just kind of pause the video, give you a chance to try them, and then I'll talk through them. All right, let's take a look. So on number 5, I have just a direct application of the formula for the derivative of arcsine. Since I'm taking the integral of that derivative, then I will be looking at the antiderivative being arcsine of x. And then I'm going to plug in my 2 limits of integration. Now, keep in mind that the range of arcsine is negative pi over 2 to pi over 2. That means you're going to get out an angle in either the fourth quadrant or the first quadrant. So the the first quadrant angle that has a positive arcsine of 1/2 would be pi over 6. We can see that from the triangle. Pi over 6 triangle. So the sine of pi over 6 is 1/2. So then if I need to translate that to the fourth quadrant to have a negative sine of 1/2, or a sine of negative 1/2, I guess I should say, I'm going to be looking at negative pi over 6 because that is how I need to name it given this range. It has to be between 0 and negative pi over 2. So that gives me a final answer of pi over 3. Number 6 is pretty straightforward. I take my antiderivative. Since it's an e to the x times a constant, it'll be its own antiderivative. I plug in the ln and the 0 and simplify. For number 7, I've got a piecewise function. So the fundamental theorem of calculus said I'm only allowed to use this theorem if I'm dealing with a continuous function. So the first thing I wanted to do was check this condition. Is this function continuous? So at 2, it's defined to be 3x minus 2, which would be 4. And that would also be the limit as x approaches 2 from the right. It's going to be 4. And so then I'm double checking if I approach 2 from the left, will I get the same thing? And I will. So I do have a continuous function. So now we're going to apply that property of integration we learned in the last lesson, which told us if we're doing an integral from 0 to 6, it's totally a legal move to break it up into an integral from 0 to 2 plus an integral from 2 to 6. And that's what we're going to need to do because we have a different equation for each of those intervals. So from 0 to 2, I'll be taking the integral of x squared, whereas from 2 to 6, I'll be taking the integral of 3x minus 2. And the rest of it is really just kind of the busy work of doing the antiderivatives and plugging in the numbers. And we are doing some fraction work, but it's not awful. All right, last but not least, what is wrong with the following? I have an integral from -1 to 3 of 1 over x squared. And then it's calculated by applying the power rule, plugging in the numerator, or sorry, the upper limit of integration and the lower limit of integration, and getting out a number. It's not an arithmetic error, I'll tell you that much. Here's the problem. What does 1 over x squared look like? Generally, I don't have labels on x's and y's here, but this is generally what 1 over x squared looks like. And this region would give us a, let's say this was -1, I guess 3 would be, way out here somewhere. What's wrong with this picture? Right. I'm basically looking at trying to calculate an infinite area because these asymptotes, these function branches keep going up and up forever. And so the basic problem is that 1 over x squared is not continuous on the interval that was given for the integration. And the fundamental theorem of calculus can only be applied to continuous functions. So at this stage of the game, this is not a problem that we could actually calculate by using the fundamental theorem of calculus. You will learn other ways to approach this in Calc 2. So something to look forward to.